Hi everyone, my name is Sepeh Rezai. This is joint work with Muhaddis Khoshnewissam at the University of Colorado Boulder. In this project, we study a simple but important question. How much 3D is actually needed for hyperspectral image classification? Hyperspectral images are very rich. Each pixel contains hundreds of spectral values, not just RGB. To classify materials correctly, we need to use both spatial and spectral information. There are two common approaches. 2D CNNs are efficient, but they ignore spectral relationships. 3D CNNs capture both spatial and spectral features, but they are computationally expensive and often overfit, especially when labeled data is limited. So we face three key challenges: accuracy versus efficiency, limited labeled data, and the need for lightweight but efficient models. This leads to our main question: do we really need full 3D CNNs? To answer this, we design a family of models with increasing 3D depth. We start with a 2D CNN, which uses only spatial convolutions. Then we build hybrid models. Hybrid 1 uses one 3D convolution layer at the beginning, so it captures basic spectral spatial features. Hybrid 2 uses two 3D layers, which allows deeper spectral spatial modeling. Hybrid 3 uses three 3D layers, capturing more complex spectral interactions before switching to 2D. After the 3D block, all hybrid models reshape the features and use 2D convolutions to refine spatial patterns. Finally, we compare all of these with a full 3D CNN, which uses three convolutions throughout the network. Importantly, everything else is kept the same, so the comparison is fair. We evaluate our models on the Salinas dataset, which contains 224 spectral bands and 16 classes. Each input is a 25 by 25 spatial patch with full spectral depth. This allows the model to learn both local spatial structure and spectral signatures. The overall architecture is shown here. We first apply a variable number of 3D convolutional layers to extract spectral spatial features. Then we reshape the output and apply 2D convolutions to refine spatial information. Finally, fully connected layers produce the classification output. So the key idea is early 3D feature extraction followed by efficient 2D processing. All models are trained under identical conditions. We use cross-entropy loss, patch size 32, and the same optimizer and training schedule. We evaluate performance using accuracy, Markov F1, and the average accuracy. We also test different data regimes, 1%, 5%, 10%, and full data to study generalization. Now let's look at the results. On full data, Hybrid 3 achieves the best performance, with about 95.6% accuracy and 95.3 Markov F1. This is slightly better than the full 3D CNN. So we already see that the full 3D is not necessary. Under limited data, the behavior changes. At 5% data, Hybrid 2 performs the best, with around 89% accuracy. This shows that a moderated amount of 3D modeling is not enough. At 10% data, Hybrid 1 performs very strongly. Looking at the overall trend, all hybrid and 3D models outperform the 2D CNN. And hybrid models consistently generalize better. Now we look at efficiency. 2D CNN is the most efficient but least accurate. Full 3D CNN is expensive in terms of parameters, training time, and memory. Hybrid 3 provides the best balance, very high accuracy with much lower cost than full 3D. We also observe diminishing returns. Adding more 3D layers improves performance at first, but behind the point, the gain becomes very small. So the main takeaways are, a small number of 3D layers is sufficient. Hybrid models outperform 2D CNN by capturing spectral spatial features. Increasing 3D depth leads to diminishing returns. And most importantly, full 3D modeling is not necessary. Hybrid 3D 2D architectures provides the best balance between accuracy and efficiency, making them more practical for real-world applications. Thanks for your time.